All right, class, let's calculate height or velocity when mechanical energy is conserved. So what does that mean? So you take a scenario, physics scenario, and we're gonna do some calculations. Another way to say it is we were going to perform some predictions. So, for example, if you knew Batman and this cart, if you knew his height, could you calculate after he rolls down this track? Could you calculate his velocity? Could we find that out? Could we make a prediction? And the answer is yes, but only if we know the law of conservation of energy. So that's the gist of where we're going, and the best way to do it is to look at some examples. So we're going to look at two examples. Example number 1, a 5-kilogram frictionless cart at rest at a height of 10 meters rolls down the track to the bottom. What is the velocity of the cart at the bottom of the track? Ignore air resistance. So we're using this cart with Batman in it and this track as an example. So first, let's note no work is being done by friction or air resistance. Therefore, we know that mechanical energy is conserved. Remember, it tells us this is a frictionless cart, and we're going to ignore air resistance. That means no work is done by friction, so there's no energy transfer. Work is a change in energy, so there's no energy transfer into thermal energy, right? Mechanical energy is conserved. Therefore, we know that the gravitational potential energy completely transforms into kinetic energy. So this completely is important. There's no leftover GPE at the end because he's at no height right there. So we're gonna start with GPE and we're gonna end with kinetic. GPE completely transforms into kinetic energy, and we could write a new equation. So what is that new equation? So I call this the conservation equation. So our conservation equation is we know that all of the GPE transforms into kinetic energy, so we could write this out in a new equation. GPE at the top is going to equal the kinetic energy at the bottom. Now let's make sure that we remember what we're trying to do here. We're trying to find the velocity at the bottom. So this is just the pathway that we get there. So how do we get velocity into the equation and height into the equation, maybe even mass as well, because those are the variables that are given to us. Remember that it doesn't tell us anything about energy in this problem. It's asking us about velocity, it gives us height and mass. But energy allows us to solve this problem, and let's recall the GPE and KE equations. So you should have these memorized. GPE equals the mass times the acceleration due to gravity, or little g, times the height. Kinetic energy equals 1/2 times the mass times the velocity squared. You guys should have those memorized. Now the gravitational potential energy, we can now substitute the variables in. So instead of writing GPE, I'm going to substitute in what GPE is made up of, which is mass times gravity, or the acceleration due to gravity, times the height. So instead of writing this, I substituted that. Easy peasy lemon squeezy. And the same goes for kinetic energy, 1/2 mv squared. I have a new equation. Look at that. So then we're going to substitute the known values. Values is the numbers that we know. So what numbers do we know? We know that the mass of the cart, m, equals 5 kilograms. We know that the height of the cart up here is 10 meters. And Batman here, okay, I can't select him. Whatever. Don't need to. You can imagine him rolling down this track. We're just going to substitute everything that we know. So we know that the mass is 5. The acceleration due to gravity is 9.8 meters per second. And the height is 10 meters. Easy peasy. We just substituted in what we know. Times 1/2 times the mass, which is 5, times v squared. So you look at an equation like this, and this is actually kind of a nice and easy algebra equation. Although it looks like there's a lot of steps to it, it's not as hard as you might think. So let's remember what our math steps are. We got to isolate the unknown variable. Our unknown variable is this v right here. V is like the x in our algebra equation. We don't know the value of v, so we keep it as v, velocity. And then we want to combine like terms. So what terms here are like? These guys here, they don't have, any x's or anything in front of them. Those are just whole numbers or those are just regular numbers that we're going to multiply by. So let's use our handy dandy calculator and just multiply those out. 5 times 9.8 times 10 equals 490. Probably could have done that in my head. Equals 1/2 times 5. I'll combine those like terms. 1/2 times 5 is 2.5. Times v squared. We're just going to keep that as our unknown. Now, let's see. Yeah, I want to combine like terms still. Here's a like term. That's a like term. So how do we get rid of this? How do we isolate that variable? So we want to isolate the variable, and it's being multiplied by 2.5. So how do you get rid of a multiply by 2.5? You divide by 2.5. This is called using opposite operations. So the opposite of multiply is divide. 490 divided by 2.5 is 196. Equals v squared. We're going to use the strategy of using opposite operations. We're going to do that again when we square root the square. So we have v squared right here. If you take a square root of a square, you get rid of it. Now that v squared is now a v, that's great, but remember, whatever you do to one side, you do to the other. Now you can turn your calculator over to the side or however you do it, but you take the square root of 196, you get 14. Now the last thing is to remember that this is a velocity, and in physics we never forget our units, and the units for velocity are meters per second. Look at that. We've made our prediction. So that means that Batman, let me try this one more time. There we go. Batman's going to start up here at a height of 10 meters, and he's going to roll down, and by the time he gets to the bottom, he's going to have a velocity, v equals 14 meters per second, because energy is conserved. Cool. So that's how you do that. Let's do another example. So what is the maximum height achieved for the snowboarder moving at 10 meters per second towards an incline? Ignore friction and air resistance. Okay, so we don't know his mass. All we know is his velocity. We know his velocity is 10 meters per second. He's going this way, and he's at the bottom of a hill. So it's asking us, how high up is he going to get? How high up? Is he going to get all the way up to the snowman? Who knows? Well, let's see. So we know that, again, in this case, no work being done by friction and air resistance. And that means that mechanical energy must be conserved. Kinetic energy completely transforms into GPE at the moment he runs out of speed. So he's going to have speed as he goes up, and as he gains height, he's going to slow down because he's moving up. And then as soon as he runs out of speed, he's going to be at his maximum height, and all of that kinetic energy will have transformed into GPE. So we're going to write our conservation equation. So he starts with kinetic energy. He's got kinetic energy at the bottom. And that's all going to become, that's going to equal his gravitational potential energy at the top. Let's recall the GPE and kinetic energy equations. GPE equals mgh. Kinetic energy equals 1/2 mv squared. And now let's substitute our variables. Same steps, same steps. Substitute the variables in. 1/2 mv squared equals mgh. Now we're going to substitute the known values. you know what? One thing we could do at this step is to recognize something. We could have done this last time, but I didn't want to add something new. Look at this. We got mass on this side and mass on that side. Let's think about this for a second. If you have the same variable on each side of the equation like this, if I divide this side by mass and cancel mass out of this side, whatever I do to the other side, or one side I do to the other, look at that. Mass cancels out of both sides. It's amazing. We never even needed mass to begin with. Mass doesn't matter. In this case, mass doesn't matter. Mass cancels out. So now we got rid of that mass variable that we didn't know. And so let's, isolate the unknown variables, combine like terms, use opposite operations, and square root the square. Those are our algebra tools that we have in our toolkit. So let's substitute the known values. What was his speed? It was 10 meters per second. So 1/2 times 10. But remember, that's squared equals 9.8 times h. So now we have our unknown variable, this h right here. That's our unknown variable. And let's solve. So PEMDAS, parentheses, exponents, multiplication, addition, subtraction. So PEMDAS tells us our order of operations. So what do we have to do first? We have to square this 10. So 1/2 times 100, I just squared that 10, equals 9.8 h, or 9.8 times h. I just got rid of those parentheses. They weren't really helping me understand the math. 1/2 times 100, that's 50. Half of $1 is 50 cents, times equals 9.8 h. Let's isolate this variable. Whatever I do to one side, I do to the other. Boom. 50 divided by 9.8. I wish I could do that in my head. I can't. I got to use a calculator. And I get the height equals around 5.1. And remember our units in physics, we never forget our units, 5.1 meters. Perfect. So we know that the height that he will achieve when he gets to the end is around 5.1 meters, given that energy is conserved. Cool. So remember your steps. You can make some flashcards so that you remember your steps. And remember this. The law of conservation of mechanical energy allows us to make these predictions. Note that in the real world, air resistance and friction will affect your prediction. How? Well, the cart that we talked about in the first example, it's going to be slower at the bottom of the track because there's friction. And the snowboarder will reach a lower height. And this is because air resistance and friction do work on these objects, removing the amount of mechanical energy they have. And this is in the real world. So in the real world, we have air resistance and friction. And so you'll see slower heights or lower heights and slower velocities as some of that energy from their mechanical energy gets transformed into thermal energy, things like that.